Hello, everybody, and welcome to another wonderful day of chemistry. So one of the useful things about using electrochemistry is it's often a very useful way to determine where chemical equilibrium occurs. So in other words, it's a good way to determine your equilibrium constant. So one of the ways that we can do this is by combining our Nernst equation with a lot of what we know about free energy and electrochemistry. So if I go ahead and measure the potential for a given reaction, I'll get a known potential. And by looking up a whole bunch of values in tables, I can figure out the standard state potential. However, one of the interesting things is that we can then relate these two to, again, the number of electrons being transferred and the reaction quotient. However, as we saw for Gibbs, there's a very unique point in this reaction, and that's going to be the point at which the system reaches equilibrium. So this should happen if you let any reaction sit for long enough that eventually the reaction quotient will equal K, and as a result, the Gibbs free energy goes to zero. However, by using our relationships in between Gibbs and potential, this also means that for an equilibrium or reversible reaction, the potential should also be zero. And thus we can go ahead and simplify our Nernst expression, because we know that our standard state potential minus RT/NF, natural log of the equilibrium constant, should also equal zero. So we can then set this relationship in between our potential and our equilibrium constant. So as long as I know one, I should know the other. And as we've stated before, you can go ahead and determine your standard state potential from essentially a lot of reduction potentials. So then this lets us determine our equilibrium constant, again, just making note of the standard state potential, which can come from a table, the number of electrons, which should come from a balanced reaction, and the temperature of the system. So let's go ahead and look at some reactions for a reaction at room temp. So we've already determined that the standard state potential for the reduction of zinc by copper has a standard state potential of 1.1 volts. Now, what would the equilibrium constant for this reaction be? So if I was just going to mix zinc and copper salts together, well, one of the first important things to do is make sure to write out your two half reactions, because this will let you know the number of electrons being transferred. So in this case, zinc is losing 2 electrons and copper is gaining 2 electrons. So we have a simple 2-electron exchange. Then we can go ahead and use the relationship in between our standard state potential and equilibrium constant. And then we have fun plugging in all of our values, including the number of electrons, Faraday's constant, our standard state potential, the ideal gas constant, again, making note that our joules cancel out here, and the room temperature system. So again, you'll note here that all of the units should cancel, Kelvins cancel, joules per mole cancel, and volts cancel. So all we're left with is a unitless equilibrium constant of 7 times 10 to the 85th. Whew, that is a big value. And let's go ahead and interpret that a little bit more physically, because again, our equilibrium constant for this expression, for this reaction, can also be expressed as the concentration of zinc ions over the concentration of copper ions, which means that if I go ahead and throw a bunch of solid zinc with copper and let it sit for long enough, I should end up having a ratio of 7 times 10 to the 85th. Meaning that once the system reaches equilibrium, the concentration of the zinc ions should be about 7 times 10 to the 85th times higher. That's a little much, but it really does illustrate the large magnitude of the equilibrium constants we'll be dealing with in electrochemistry. So when you see a potential of 1, we're talking with equilibrium constants, often with orders of 10 to the 50th or higher. So these reactions are very product or reactant favored, which does have some advantages when we're talking about equilibrium systems and ice tables, but does emphasize just how much energy and how much favorability is floating around in these reactions. So next time, we're going to go ahead and focus on how you can use reactions like this reaction of zinc and copper salts to generate some energy. Until then, take care.